Hello and welcome to this webinar from SCIA. Today's topic is seismic calculation and how it is applied for buildings with SCIA Engineer. My name is Shad Al-Alam and I work as Customer Service Engineer at SCIA. Before we start today's webinar, I will explain a little bit how GoToWebinar works. You might need to adjust the sound, and you can do that by using the sound check in the audio box in your GoToWebinar. Feel free to ask any question in the chat box and we will reply at the end of the webinar. Also, please note that this webinar will be registered and you can rewatch it by going on our YouTube channel or on our website. Now, let's have a look at today's content. We will start by calculating the iron frequency of the structure, and then we will talk about the two methods of seismic calculations implemented in SCIA Engineer, and those are analysis using the equivalent lateral forces or ELF and the modal response spectrum analysis, and we will see in details the difference between these two methods. After detailing the analysis methods, I will discuss the accidental eccentricity and how it's applied in SCIA Engineer, the creation of seismic combinations, and last but not least, the results related to seismic analysis. So first, we will start by calculating the iron frequencies of the structure. In order to do that, we will have to start by creating a mass group where we will generate a mass either by an automatic generation using defined load cases or by manually inserting them. We should then combine the masses associated to permanent gravity loads and variable gravity loads by creating what is called combination of mass groups in SCIA Engineer. I will now switch to SCIA Engineer in order to show you how this is done. Okay, so this is our project for today. It's a building composed of concrete and steel. So I have the first, here I have the floors that are in concrete, and I have the last 2 or 3 floors in steel. In order to calculate the iron frequencies and to start, I have to go to Project, Functionality, and I have to activate the Dynamics functionality and Seismic. So I click on OK. And once I have activated this functionality, I can see now that I have the Dynamics menu that is now available. And here I can, for example, in masses, I can insert a manual mass. In mass groups, I can create mass groups, and I can also create combination of mass groups here. So I'll first go to mass groups. I have the first mass group that is bound to a load case, which is the self-weight. Okay, I'm gonna leave it like that. I'm gonna create a second mass group that is bound to the permanent loads, and a third mass group that is bound to a load case, which is the Q, the variable loads. I can add a description, for example. Here I will put Q, this is J, and this is self-weights. Okay, once this is done, I can close now, and I can go to combination of mass groups, and here I can create a combination. I will add all here, and I can apply a factor coefficient, for example, of 0.15 to the Q, like this, and I will name it self-weight plus E plus 0.15 Q. Okay. With just these simple steps, I can now calculate the iron frequencies of the structure. But before doing that, I will have to go to the solver settings, and here I can define the number of iron modes. I will, for this example, I will choose, for example, 35. Okay, and now I can run the calculation. I have to choose modal analysis, and I click on OK. Okay. Okay, once the calculation is finished, we can go now to the results menu, and here I can go to calculation protocol and choose as type ion frequency and click on preview. So I will have here the calculation protocol. Here I have the table for the method that I used, the number of frequencies, and the combination that I used. And here I have the table of modal participation factors, where I can get the modes, the period and frequency for each mode, and the participating mass. And here at the end I have the total participating mass for these modes that I chose. I can also go to the form structure, and in type of loads I have to choose the mass combinations. Of course, here I have to choose which mode I want to see the deformation. For example, for the first mode, I click on refresh, and here I can see, for example, in red the deformed structure. I will deactivate this. And here, for example, if I change the view, I can see the deformed structure for mode 2. If you want, you can also see an animation for this by going to View, New Animation Window, and here, for example, I can see an animation for this mode. Okay, now that we have calculated the ion frequencies of the structure, we can start by defining the seismic action. We will start with the method of equivalent lateral forces, or ELF, that was implemented in SCIA Engineer from version 15.2. Seismic ELF analysis is the most well-known method for seismic analysis of structures. Although it is quite conservative, its simplicity makes it a very popular method for seismic design. The ELF method is a static analysis method. However, using it in SCIA Engineer requires the input of some data related to dynamic analysis, like masses, and at least one combination of mass groups must be defined, as the calculation of the seismic equivalent lateral forces is based on the distribution of masses in the structure. The calculation of storey forces is based on the definition of storeys as well as the reduced system, which must therefore be defined in order to allow using the ELF analysis. According to Eurocode 8, some criteria need to be met in order to use this method. The first one is regarding the fundamental period of the building according to Article 4.3.3.2.1, and the other criteria should be regularity in elevation according to Eurocode 8 Article 4.2.3.3. We can also see here the ASCE requirements for using the ELF method. By choosing this method, SCIA Engineer will calculate the base shear force that depends on 3 factors according to Eurocode 8, or using the following formula from the ASCE. There are 3 calculation methods possible: maximum acceleration of spectrum, manual input of fundamental period, and according to a selected ion mode. Once the base shear force is calculated, SCIA Engineer will redistribute this force on all the height of the structure using one of the following 3 methods: linear distribution, proportional according to a chosen modal shape, or polynomial described in the ASCE. Also, in order to use the ELF method, we have to activate the reduced model, or IRS. I will talk more about the IRS model later on. I will now go back to SCIA Engineer to show you how this is applied. Okay, so I will now show you how to apply the equivalent lateral forces in SCIA Engineer. So of course, after defining the mass groups and the combination of mass, I will have to go to library in order to find my spectrum. So I have to go to library, roads, and seismic spectrums. I will closes, and here I can define, for example, input. I will use the Eurocode, and I can change the code parameter, for example, and choose, for example, an acceleration of 1.1, for example, and Q of 1.5, and I will choose a subsoil type B. Okay, now I have this seismic spectrum that I created, and once I have created the spectrum, I can go to load cases in order to create my seismic load cases. So I'll create a new load case that I will call seismic following the X direction. The load type is dynamic, and specification is seismicity. And here I can choose, for example, direction X. I have to define a response spectrum. Of course, for this case, I only have this option because I created only one spectrum. And for the equivalent lateral forces here in the ELF method, I can choose, for example, the three methods that I have previously described. So I will choose linear distribution of acceleration, and the seismic force from, I can choose maximum acceleration of spectrum, and input fundamental period. I will choose maximum acceleration of spectrum. I will create a new load case, which is the seismic load case in the Y direction. For this case, of course, I will have to deactivate the direction X and activate direction Y. And of course, I have to pay attention to change the factor to 1. Okay, now let's have a look at the second method implemented in SCIA Engineer, and that is the modal response spectrum analysis. This method can be used for the structure that do not comply with the prerequisites that we have defined earlier for the application of the ELF method, and this is the method used by default in SCIA Engineer. But also for these methods, we have some criteria that need to be met, such as the sum of the effective modal mass for the modes taken into account amounts to at least 90% of the total mass of the structure, and all modes with effective modal masses greater than 5% of the total mass are taken into account. These criteria are used in order not to underestimate the seismic load, and the first criteria is normally the criteria that causes the most problems or difficulties to achieve. So, how can SCIA Engineer help you achieve this criteria of obtaining the 90% participating mass ratio? For this, we have two tools that we can use. The first one is the palliative methods, and also the second one is the reduced model method. So, what are these palliative methods? There are three different methods in order to take into account the modal masses in the analysis. Participating mass only. This method takes into account the calculated mode's mass only, so you consider only the participating mass. It's like you are telling the software to not include all the mass in the calculation. Missing mass in modes. The program recalculates the missing mass in modes that has been already computed by increasing the results obtained from the calculated modes. For example, if we get 80% participating mass, the results will be amplified by 1 divided by 0.8, so equals 1.25. The residual mode, the missing masses are associated with rigid parts of the structure and therefore are not vibrated. In fact, these masses are subject to ground acceleration as a rigid body. Residual mode method install the missing mass as a weight. The result of this load case is handled as an extra mode. Okay, so here we have a comparison of shear force results in a wall with only 80% of total mass mobilized. We can see that when we use the participating mass only and the residual mode, the results are very close. But using the missing mass in modes, the results are amplified and are much more important with a value of 456. Also, to compare for this same example, if we reach 90% criteria, we will get a force of 380.4 kilonewtons. So we see that the residual mode is not that far from this value. Okay, the second tool to obtain the 90% participating mass is the use of the reduced model analysis, or IRS. The actual tendency in final element structure analysis is using the full 3D modelization of the considered structure. SCIA Engineer obeys that rule as structures are usually modelized in 3D using beam and shell elements, including buildings. Once a detailed 3D modelization is ready for statistical analysis of a structure, it's natural to use it also for dynamic analysis, and more specifically for seismic design. Once a detailed 3D modelization is ready for statistical analysis of a structure, it is natural to use it also for dynamic analysis, and more specifically for seismic design. A typical issue of full 3D model is that seismic design regards mostly the overall behavior of the structure, whence the full mesh of the structure provides a lot of information about local behavior, for example. More specifically, for modal analysis, the full mesh lets appear local vibration modes, which are irrelevant for the overall seismic response of the structure. It appears hence logical to use a different, reduced mesh for dynamic analysis. Here, for example, we see an example of local vibration modes. And here we see the global modes that are used for dynamic calculation. SCIA Engineer is the only software where an improved reduced system IRS method has been developed, which takes into account not only the stiffness matrix of the system but also the mass matrix during the condensation process. That method proved to give excellent results for dynamic analysis, with both modal analysis and direct time integration methods. The algorithm implemented in SCIA Engineer used the IRS method and consists of 3 steps. The IRS method is used for condensing the mesh of the analysis model. The modal analysis is performed using the reduced mesh, which has typically 1000 times less degrees of freedom than the original full mesh. This makes the calculation of eigenvalues massively faster on large structures. Then the results of the reduced system are expanded to the original full mesh, allowing for output detailed results in the entire structure. What are the advantages of the IRS method? The advantages are: 1. Local modes in all structure elements are implicitly removed due to the elimination of unwanted degrees of freedom. 2nd, we have better conversions of the modal mass. And 3, the computation time is reduced due to the drastic reduction of the number of degrees of freedom. In order to use the IRS model, it's very simple. The user has to define stories and activate the IRS model in the solver settings. Okay, let's compare the results between a standard model and a model with the reduced IRS model activated. We see here that using the same number of ion modes, we have obtained 91% in the IRS model, while in the standard model we only reached 78. We can also see that we get the same frequency in both models, so the IRS model only shows the global modes of the seismic analysis. In SCIA Engineer, we also have another tool that allows us to modify the behavior of certain elements without changing the material behavior, and this is done by using the property modifiers. These property modifiers can be used for static calculation or in seismic calculation. They can be used to modify the self-weight of certain elements by adding a factor, by modifying, for example, also the stiffness of certain elements in a way to consider cracked elements, for example, and also to modify the mass of certain elements, for example, to disregard the mass of immobile elements. Property modifier can be used for 1D and 2D elements. We also have some tools related to results, such as signed results and results related to displacement. To obtain usable values of resulting forces, a possibility is the so-called signed results method. It consists of applying some signature scheme to raw results of the modal superposition. A classical approach uses the sign of the most significant ion mode. The signed results could be interesting, for example, if you wish to get the resultant forces in a wall for seismic load cases, or to look at particular results such as the support reactions, for example. We can see this in this example where we can see the uplift force on part of the walls and supports. Okay, and finally, to finish this part related to spectrum analysis method, a remark concerning the displacement results. The displacement due to seismic load cases should be multiplied by Q, which is the displacement behavior factor that we have introduced in the response spectrum. If you do an elastic calculation in SCIA Engineer with a Q equal to 1, the displacement given in SCIA Engineers are okay. But for other cases, we should readapt the displacement values either by adding a manual correction factor for the combination or by creating separate load cases for the results of efforts and displacement. Okay, I will now talk about the accidental eccentricity and how it's used in SCIA Engineer. Most of the seismic codes require that structures are checked for torsion due to mass eccentricity, including an additional eccentricity, so-called accidental eccentricity. This is required to cover inaccuracies between the real structure and the model, as well as the fact that masses that are linked to service loads may vary during the life of the structure. Two types of eccentricity must be distinguished for the analysis: the structural eccentricity, which is automatic in a 3D model, and the accidental eccentricity. The accidental eccentricity accounts for inaccuracies in the distribution of masses in the structure. Design codes usually takes into account an additional mass eccentricity that is defined as a fraction of the size of the structure. In the Eurocode, for example, the accidental eccentricity for a given floor is defined as 5% of the width of the floor perpendicularly to the direction of the acting seismic action. In SCIA Engineer, the software will calculate Fj, the horizontal force acting on storey J, and then he will multiply it by EAJ, which is the accidental eccentricity of storey J, to get the torsional moment for the storey. There are three methods for the calculation of the storey force. 1. Linear distribution of accelerations. In this case, the distribution of acceleration is assumed to be linear, proportional to the height. The reference level is the overturning level defined in the seismic load case properties. 2. Distribution of accelerations from ion shape. In this case, the distribution of accelerations is assumed to be proportional to the displacement of the structure and the relevant mode shape. The user must specify the reference mode. When the mode shape selection is set as automatic, the program selects the mode that has the highest modal mass in the direction of seismic action. And 3. Acceleration from modal superposition. In this case, no distribution key is used. The accelerations are obtained directly from the seismic load case after modal superposition. The acting forces on storeys are obtained with the following formula. This approach is not described in the Eurocode. It is more conservative than the other approaches, as it uses an envelope of accelerations instead of a distribution of the resultant base shear force. However, it has the advantage of covering cases where higher order modes cannot be neglected for accidental eccentricity. In SCIA Engineer, we have to activate the IRS model in order to add the accidental eccentricity. Okay, let's talk about seismic combinations. In SCIA Engineer, the seismic combinations are very easy to use. So after creating the seismic load cases, we have to add these load cases to a load group type seismic, and then in the combination menu choose the type EN seismic combination, which is according to the Eurocode. Note also that US combination are currently under development and will be available soon. Okay, so I will now start with the modal response spectrum analysis, and I will start by talking about property modifiers that I have talked about before. In order to use these modifiers, you have to activate this functionality. So we have to go to Project, Functionality, and tick the functionality Property Modifiers. and then you have to go to structure, and in structure, model data, and in model data you have property modifiers for 1D elements and 2D elements. In this case, I have already added some property modifiers to my walls. For example, for this wall, I have added a stiffness correction factor of 50% for the actual stiffness to consider that the element is cracked. The first step in a seismic analysis is to check the participating mass. So for this project, I have already calculated the project. I have already ran the model analysis, so I can go to results, calculation protocol. I have to check the type ion frequency, and I can see a preview. I can see here that I have 71% participating mass in the x direction and 70% in the y direction, which is of course not enough. So in order to reach the 90% rule, as we discussed earlier, we can either choose the palliative methods or the IRS model, or we can use both, of course. I will start by using the IRS model, and as I have stated before, in order to use the IRS model, we need two things. We need to define stories, and we need to check to activate this functionality in the solver settings. For stories, we have to go to the line grid and stories, and in this case I have already defined my stories. It's simple. We can do that by going to stories and defining the bottom and the height of the floor, and after that we can go to the calculation menu, solver setup, and simply tick use the IRS or the improved reduced system method. And that's it. And now we can run the calculation. Okay, we can now go to results, calculation protocol, ion frequency, and check now the participating mass. We notice here that using the IRS method, we have now reached 92% of participating mass, which is more than the 90% required. So we no longer need to use the palliative methods also. Okay, now we can create our seismic load cases. So to do that, we have to go to load cases. We have already predefined here two seismic load cases, SX and SY. Of course, I will start with seismic load case in the direction of X. Keep in mind that the load type has to be dynamic and the specification need to be seismicity. We have to take the direction of this seismic force, and we have to define a response spectrum that we have done in the previous example. Here we can choose the modal superposition method, so either the SRSS or the quadrative method, and we have to define a damping spectrum, of course. We can also here use the signed result, for example, and we have to define the mode shape. And we can here choose the accidental eccentricity if we want to use it. Of course, by default, it is disabled. We can choose the type of accidental eccentricity. For our case, I will choose, for example, linear distribution of acceleration. And we choose the eccentricity that is defined by the code. I will do the same thing for the y direction. And notice here the creation of two static load cases because I ticked the accidental eccentricity. Okay, so now I have to create my combinations. I will go to combinations menu. I will create a new combination, Seismic for example, and type I will choose the EN Seismic in order to use the seismic combinations according to the Eurocodes. And I will add all the loads that I want to consider. As I previously stated, for example, this combination will be used for internal forces, and I will copy this combination and I will call it displacements. And for this case, I will take the active coefficient and multiply the seismic load cases by the Q factor that we have defined in our spectrum, which is 1.5. And I can now run the calculation. Okay, so let's take a look now at the results. We can go to the results menu, and here, since we defined stories, we have a new menu, stories. Inside we have summary results and detailed results. So summary results are the results related to the IRS model. We can, for example, take a look at story data for a mass combination, and I will choose, for example, for all stories. I will change the view and refresh. Here we have here we have the mass for each story and the center of the mass for each story. We can also take a look at the preview to have a table. Also, we can take a look, for example, at the results for a load case, for example, the seismic load case in the x direction for the acceleration, for example. Refresh. We can also check the displacement and the interstory drift. We can also look at the detailed result. Detailed results are calculated for dynamic and static load cases. So, for example, we can check here in the load cases. We can choose any load case that we want. We can check, for example, for the seismic combinations. I will choose seismic 1, the internal forces. I can check per story or per member. So I will choose, for example, result type internal forces, choose N. I will select floor number 2. And in the selection, I can choose, for example, a single story and choose floor number 2. So here we can see that we have the result per member, so per column and per wall. I can also check the resulting force per member, for example. For a seismic load case. And here I can see, for example, Fx and Fy, since I have ticked Fy also. So I can have many results, as many results as I want per element. Another option for results is to see, for example, the results per story. For example, if I choose here, instead of member grouping, I will choose per story. I will choose, for example, the horizontal forces Fx and Fy, and here I can choose all story. So here we can see the resulting forces per story for the seismic combination internal forces. So here comes our last part of this webinar, the results per story and the resultant forces. As we saw in SCIA Engineer, we have several options to see the results. We can choose to show a section in 2D member, or we can show the resultant per story for certain element of the floor section, for example. We can check the internal forces in structural elements. We saw that the resultant, to see the results, it is synthetic, walls and columns on the same drawings. We have a simple choice of the level of the section or the cut. We have the total and average value per wall. We saw that the story results are suitable for static and seismic results, and suitable for load distribution. So to summarize this webinar, we saw that for the ELF and model response spectrum analysis, we have some common settings, such as generating the masses and combinations, calculating the ion frequency, generating the response track spectrum, and the creation of seismic load cases. Then we have some specific settings for each methods. For example, for the ELF methods, we have to choose the calculation type ELF, and we have to activate the IRS model. While for the model response spectrum, we have the possibility to choose a palliative method or IRS method. These methods will help us achieve the 90% participating mass, and we can choose the signing of results. Then other than that, we have some other common settings, such as adding accidental eccentricity and the automatic generation of seismic combinations. What about the required modules for seismic design? For the ELF method, it is a complementary module sold separately, which is the ESAS 0.26. And to calculate by using the model response spectrum analysis, this method is included in the professional and expert editions and in the advanced steel pack. And of course, you have possibility to add this method using the ESAS P.01. Please feel free to contact your sales representative or send an email to sales@scia.net. We reached the end of our webinar. Thank you all for your attention.